The standard solar model operates on a specific premise. Stellar nucleosynthesis relies on the continuous fusion of hydrogen into helium. This process, known as the proton-proton chain, is the theoretical engine driving the life of every star. The primary barrier to this model is Coulomb repulsion. This electrostatic force dictates that identically charged particles, like positive protons, mathematically repel one another, preventing them from meeting. Astrophysics relies on quantum tunneling to bypass Coulomb's law. A particle penetrating a structural barrier, it lacks energy to cross. But these models demand unobserved core temperatures. In simulations, the actual probability of this event occurring naturally remains remarkably close to zero. Nathaniel Faxon Cherier proposes an alternative based on different mechanics. The critical building blocks for fusion are deuterons, atomic nuclei containing one proton and one neutron. Cherier's model suggests these deuterons do not originate from direct proton fusion. Instead, he identifies the origin of these deuterons as a continuous interaction between trapped, ultra-high-energy gamma rays and neutrinos already circulating within the core. Reconciling the multi-billion-year lifespans of stars with classical physics requires setting aside the tunneling assumption. This shift moves the focus from matter-on-matter collisions to photon-neutrino kinematics. The interconversion of protons and neutrons in the core is governed by beta decay. Beta decay is a radioactive process where a neutron transforms into a proton, or a proton into a neutron, releasing energy in the process. Inside a stellar core, beta decay reaches perfect balance. The conversion of protons into neutrons is matched exactly by its opposite. Because this cycle is perfectly balanced, beta decay alone cannot explain the high volume of neutrons. A secondary mechanism must exist. The byproduct of these pervasive beta decay events is the constant emission of trapped gamma rays throughout the core. This graph illustrates the energy spectrum of those emissions. While the peak intensity sits at 10 giga-electron-volts, the curve includes extreme spikes reaching as high as 467.7 GeV. The stellar core is an environment saturated with ultra-high energy radiation. These gamma rays provide the energetic fuel required for a new method of neutron generation. Cherier established a specific minimum energy threshold for this process. A trapped gamma ray must exceed 1.88 GeV to initiate the synthesis of a deuteron. First, three high-energy gamma rays collide, creating a proton and neutron. This creates matter directly from radiation. The second pathway involves two gamma rays and one neutrino. Third, one gamma ray interacts with two neutrinos. All combinations synthesize a proton-neutron pair. This leads to an astrophysical puzzle. If stars are flooded with neutrinos, why is direct interaction between neutrinos and standard nucleons so difficult to detect? Cherier's answer is consumption. The local neutrino population is rapidly depleted by these deuteron-forming interactions, leaving few neutrinos available for standard nucleon collisions. These high-energy gamma rays act as the primary catalyst for nucleosynthesis. By synthesizing deuterons from radiation and neutrinos, the core renders tunneling models unnecessary. Shifting from particle mechanics to the macroscopic core reveals a larger energy cycle. Cherier argues that unidirectional fusion reactions would deplete a star's fuel sources too quickly to sustain its multi-billion-year lifespan. Stars emit vast quantities of neutrinos, which serve as an empirical indicator of ongoing nuclear fission occurring alongside fusion. This loop defines the star's efficiency. Fission events provide the high-energy particle impacts necessary to induce further fusion, creating a self-sustaining cycle. These fission impacts drive the pervasive beta decay that fuels the gamma genesis mechanism, ensuring the core has a constant supply of neutrons. Stellar longevity is the result of this dynamic fission-fusion cycle powered by gamma-ray kinematics. The continuous gamma genesis model also explains the final stages of a star's life. Because gamma-neutrino interactions do not depend on specific temperature or density thresholds, neutron production continues even as the star ages and fuel levels change. This diagram shows the core's resistance to gravity, electron degeneracy pressure. This quantum force arises when tightly packed electrons exert outward pressure. As gamma genesis continues, accumulating neutrons shift the equilibrium, weakening electron pressure and allowing gravity to compress the core. Eventually, the internal pressure from pure neutron density becomes so intense that it overcomes electron degeneracy, physically shedding electrons from the core. As the collapse accelerates, heavy elements are ejected, carrying the remaining protons away from the center of the star. This process reveals that neutron stars are the inevitable conclusion of unchecked gamma genesis. What remains is a core of pure neutrons, left behind after protons and electrons have been systematically expelled. These findings transition from the life cycle of stars to the future of energy production on Earth. Modern fusion reactors struggle with plasma containment because they use the flawed proton-proton tunneling model. Cherier's model suggests an alternative: gamma-ray-induced fusion. This architecture uses gamma-ray emission arrays to target a solid core. By utilizing direct photon-nuclei interactions, this design bypasses the need for high-temperature plasma containment entirely. A second concept, neutrino-catalyzed fusion, would use focused neutrino beams to artificially synthesize deuterons for energy production. Finally, fission-fusion hybrid reactors would replicate the stellar fission loop within a containment vessel, providing a sustainable energy source. Proving the gamma genesis mechanism would provide the mathematical blueprint required to achieve stable, infinite energy.